All right, so I'm Mike and Edison. We're from Facebook's Canopy team. And we're going to go through and just do sort of an overview of Canopy, sort of focused on how it differs from open tracing, and really sort of the standard, Xtrace Dapper model that's just entirely span-based to start. And then we're going to dive into sort of probably another unique feature of the stuff we do, which is we have a really robust and sophisticated way of doing, of essentially doing processing on an individual trace, in aggregate, in batch, or even on an individual trace programmatically. And sort of we'll go into that and like why we need to do that or think we need to do it. So here we go. So basically, Canopy is our unified tracing platform, right? It spans not only sort of the broad, traditional distributed trace sort of world, but also we use it to get detailed traces of individual platforms like our web tier or our mobile tier, right? And so we have like one tracing platform that gets us both of those things. We've got instrumentation in C, C++, Python, Java, PHP, which are the common language we use. It's integrated into our RPC and dub stacks and so on. And then we also ingest like mobile data from like a different format that we translate into this, so we can sort of see everything in the same set of tools and work with them through the same set of tools. And then Edison's going to be talking about the trace streams processing framework, which lets us run custom code to extract, aggregate data and also explore individual traces because they can get quite big. And then we've actually got a separate team that does single trace and aggregate trace visualizations as well. So, we have a lot of the standard visualizations, but we sort of have a really customizable tool for doing that. The Canopy data model is actually really different than sort of the traditional Dapper Xtrace model, which is sort of, based on a tree of spans, right? And really represents an RPC stack, right, to first approximation. I mean, that's sort of what you get there is sort of an RPC call stack or something like it. Ours is actually the sort of the basic thing in ours is actually just this sort of event. And we have a set of events that sort of are put together in a backend we have to reconstruct a trace. And we have actually explicit edges between one of the pieces of our data much or points, instead of just having, a parent-child relationship between spans, right? And I've got a picture of this later. And then we also have the ability to, annotate anything in the data model and also have like type metadata for like counters and stuff like that, which is pretty interesting. So this is basically what a trace looks like to us. We split it up into a set of execution units. And an execution unit is just something that has a consistent clock, right? So it's something where, if something happens at time 100 and then time 200, we at least know that the thing that happened at time 200 happened after the thing that happened at time 100, right? But that's really what it is. And it can represent like a thread in an application, or it might actually represent all of the things that happen to process an individual service request, right? As long as the clock's consistent, we can model it using an execution unit, and we do use it in both of those ways. An execution unit has a set of blocks in it, and blocks are sort of the thing in this model that are the closest to spans, but they're not quite spans. Blocks are just a chunk of time on that execution unit, and though you don't see it in this picture, we actually allow them to overlap as well. Blocks have points on them. A point is just an individual point in time. Oh yeah, the animation part. So a point is just an individual point in time. And then the way we actually represent happens before, happens after explicitly, like you would do with a parent, span relationship, that's probably going to keep happening, isn't it? The way we represent that is through actual edges between points, right? So those are the 5 objects in the data model: execution units, blocks, points, edges, and then annotations. And that's what comprises a trace. The interesting thing about this is it's richer, right, than just having spans. It's good for expressing both a broad distributed trace and a really detailed view of an individual system, but it's also a lot more complex, right? So there is a bit of a trade-off there. So this is just an example of how the events map to the data model. It's not all of the events that we have. We've got more now, but essentially what we have is we essentially at the lowest layer of this, we have a wire protocol that splits up into events like, call, receive, create block, create point, create edge, end edge, things like that. And then what we're doing is in the backend system that we have, we're taking those events, we're reconstructing them into like a trace object model. We're sort of like filling in gaps by inference for like when events may have gotten dropped. And we're just persisting that, right? So we can access it later. Okay. So, like this is just sort of an example of how some of the existing events, map to the objects in the data model. This is actually kind of from an older version of the protocol. We've sort of modified it over time to be a little more flexible. So one of the other nice things about this is explicit edges are actually useful for modeling all sorts of async things, right? So here, like we've kind of got like this synchronous like schedule, like right here from here, right, from the left arrow to the right arrow is kind of like, the synchronous thing where we're fetching a resource and we can model that with edges, right? And then, so are these, right? But then now you've got like this sort of schedule here that's saying, hey, go and do this in the future, right? And we can model that with an edge as well, where we can just sort of have a block that has an arbitrary number of edges coming out of it that say, go and do these things in the future. And then we can still track happens before, happens after through that, right? And we can sort of infer causality from that when we need to. So that's actually one of the neat things about it that makes it a little bit more flexible than just sort of the span-based model, where it's a lot easier to, model a tree of RPCs, right? Here you can sort of model, more arbitrary, happens before, happens after relationships. And then this is actually an example of one of the things we do with that, which is like figuring out like this happens to be for our dub tier, like what are the things that are actually on the critical path of a page load returning, which is like a really important thing to know if you're a performance engineer, right? But this is sort of an example of like a really deep dive into like an individual system, right? Or an individual web server essentially, where we're sort of using this to go and model out like in pretty great detail what's going on there, but then also compute, well, what's the critical path, right? That's in the way of somebody getting a response back. So really basically what this is representing is, so what that's actually representing is like some computation that's going on, right? So what this is really saying is, hey, like, I requested some resources. This other thread essentially, or really execution unit, requested some resources. They returned in here and received one, here and received two. Now you can see this block is the one that's actually working with them. It is sort of what this is trying to show, right? So it's sort of, it got the stuff it needed and then it's working with it. The duration of the request. So, okay. So in this case, the duration of the request resources block doesn't represent anything terribly interesting since the answers are coming back asynchronously. So in this particular example, it actually just sort of represents how long it took to fire off the requests. But if this was synchronous, what it would represent is how long it took to get the response back. So yeah, so then you can see like the use received one, use received two. That's where the CPU is actually doing stuff with, that. And then this sort of lets us actually go and like make sure that we have the asynchronous bits sort of slotted in the right spots. So the CPU is always busy, for instance, right? Like this sort of view. Right. And then that's sort of finally like, now we can see that, okay, like this block, right, was using the thing that was asynchronously returned from receive one. So you can sort of see the flexibility of the model where we can like trace, through all these asynchronous executions, like trace what was happening and, make sure it lines up in a way that we're using the CPU efficiently. And then finally, all that flexibility, like this is, at least in my opinion, kind of the main cost of it is like, it's hard to give someone like the data model directly and be like, hey, like have fun, right? Because it is a reasonably complex data model. So one of the things we have to some extent and are continuing to build out is actually this sort of instrumentation stack, so that in sort of like the common pieces of infra that we have, say like the 80% use case is just kind of covered through this high level API where like people just call like create point or something. And under the hood, right, under the scenes in these lower levels of instrumentation, it's just keeping track of pointers to like the active part of the trace. And like, you know, most people that are using it just say, oh, create a point, right, create a block, and like that's it. So, you know, if you're working in, you know, like our RPC framework, you know, that works. If you're doing something more interesting, right, or something that's less standard, we have this sort of toolkit to create, you know, your own custom instrumentation such that people can continue to use that high level API. And then you sort of go all the way down the stack to, you know, this, just an actual, you know, that model I showed you as an object model, just a standard, you know, just a standard sort of object model. And then finally, we've got a sync layer that's doing nothing but like taking that, translating into events and flushing them across the wire. So it's kind of like, you know, in order to really make this practical and friendly enough, and work across a somewhat heterogeneous environment, you kind of need these layers of instrumentation so that people can sort of hook in at the easiest one, you know, they need to use, and that sort of most people can do what they need to do with the high level one, but then other people sort of have to go down the stack and use lower and lower levels. And then we kind of have to build that across a few different languages. So to me, that's sort of like one of the biggest costs is just like the complexity of the model makes it harder to understand, harder to work with, and just sort of, you know, gives, there's some additional, you know, mental stuff people have to do to understand it. So yeah, that's my part. Now I'm going to hand off to Edison, who's going to talk about our, you know, what happens once we have these traces. And I'm going to trip over that.
Yeah. So Michael did a great job of covering the first problem that we have at Facebook. Basically, how do we get data into traces? Because traces are used to model performance information and whatever information you want. And if you don't have data, you have nothing. The second problem that we have spent a lot of effort on is how to get data out of traces. Because traces for us represent some heterogeneous systems, a lot of which have very little minor tweaks on a standard translation between what's happening and how it's represented in trace. And because of these minor tweaks, we can't provide just like the same set of tools for everyone. Instead, we need to be in a state where we can actually empower people to write analysis on top, write tools for building analytic tools on top of tracing. So we've talked to a bunch of companies, a bunch of outside folks doing tracing. And one question we always ask is, how do you make sense of your traces? How do you use your traces? And a lot of times the answers we get back happens to be, you know, someone takes 5, 10 traces and just looks at them and sees what goes wrong. And I think there's definitely a solution for a specific set of problems. But at the scale of Facebook, let's say we gather like a trace per second, or rather, let's say we gather roughly about like 1 billion traces a day. And if you were to like mentally just open a trace, look at it, like consume this information all within the span of 1 second, take a person 32 years to actually go through a day's worth of traces. And if you want to hire employees to do this, like it takes a company the size of Facebook to consume 1 day of Facebook's traces, working 8 hours a day. So obviously not a scalable solution if you're trying to find a lot of signal from your traces. And added to this, you know, processing 1 trace per second mentally, impossible. Like opening a trace sometimes even takes longer than that, just loading it. And this is actually a really important problem. It's a problem that we tried to tackle once and did a terrible job of. So the second time we did it, we went through and we actually formalized what exactly is the problem. And getting the problem statement correct, obviously, is a very important part of a good solution. So I want to be crisp about what exactly we try to solve with our trace processing systems. The problems are, 1, traces contain data, but individual traces and looking at them, opening even like 5, 10, 100 over the course of a day, not really that useful for some of the problems that tracing is designed to solve. Second problem might be more specific to us, especially using events and not a more constrained system like spans. Traces model things differently. The little tweaks that I talked about on top of a standard model, they actually make analysis way harder because the thing that you build for A doesn't necessarily work for B right out of the box, and you know, counting for then C, D, all the way down the alphabet can be a problem. And the last part is one that we've learned through trial and error. We do not want to be on the critical path for analysis. We, as in the Canopy team, we in the past have been very involved in helping people understand how to take these tools and build traces with them and then build analysis with that. What ended up happening was we ended up being the domain experts in their traces, which meant that any time someone needed to debug, I don't know, like HBase, they would come to us. And we don't really have necessarily a lot of domain knowledge in HBase, especially not kept current as time goes on. So the solution that we found is we provide a set of analysis tools flexible enough to be used in any use case. And more importantly, that we design these tools around the types of analysis that people tend to do with traces. So we went through our customers, we did a bunch of feedback, and we kind of found that we distilled down the type of analysis that people do with tracing, the things that they want to get out of traces, into 3 primary big use cases. One is a single trace use case where you know there's a problem and you know you have some traces that are representative of that problem. And you're just like opening traces, you're like, what's going on here? And to do this well, you kind of need 2 things. You need to be able to have people explore traces easily and perhaps to be able to even visualize traces. And tying the 2 together makes for a powerful tool. The second thing is to be able to then, once you've explored a couple traces, to kind of be able to distill a signal from there and then see if you can map that signal over a large corpus of traces. Because at the end of the day, you open 1 or 2 traces, you might get some signal, but like, is that representative? Like, who knows until you actually test it out over, some representative sample of everything. Thirdly, once you have some sort of high signal analysis, we found that people actually really are interested in taking that and running it continuously over all traces coming in, or whatever traces that they care about. The reason being is that, for instance, people build alarms, build other tooling on top of tracing with this kind of scheme because they kind of define the set of traces we care about, and then this signal that I extract from it, which then can be used in other tools to build much richer analysis on top. The thing that we realized with all 3 of these cases is that the main issue with existing tooling is that while these are disparate use cases, it ends up being the same people trying to solve one specific problem in all 3 of these use cases. They're just tackling different aspects of that problem with each different tool. And so what we found to be the most important takeaway is that for the thing that ties these tools together, whatever people use to get signal out of traces, they should be able to write it once and use it everywhere. Because as soon as you tell someone, okay, here's how you look at this tool, use this tool to look at traces 1 by 1, and you have to redo all of your efforts to look at it in batch. And if you want to do it in a stream, like, learn a new language, they run away screaming. So what does the single trace analysis typically look like? Well, the most important takeaway that we've learned from the single trace analysis use cases is that exploring traces are hard. Like, opening a trace and looking at it visually, even the problem of taking a trace and presenting it visually is a hard problem. And it's a problem that's really hard to get right every time. You can build signals based on past, what other people found important in the past, but at the same time, does that work for every future problem? Maybe, maybe not. What we found to be important is that as long as someone can explore the trace and then to be able to use a combination of viewers and interactive programmatic analysis, that they can actually combine those in a way that can extract signal out of traces relatively well. So for instance, someone might take a look at something like this, and let's say these green blocks represent DB fetches or something. They're like, 3 separate serial DB fetches. That looks weird. Can we parallelize it? It's important to be able to then go and say, okay, how long is this actual DB fetch? How long is this taking per trace? Is this actually worth looking at? to be able to like answer that question in a interactive environment. And for that one, we picked IPython notebooks. And to be able to look at in viewer is a powerful combination. The IPython notebook is actually incidentally a great tool for doing something like this because it almost has no cost of setup. Like all you have to do is know Python. And a lot of data analysts, the people who, if you want to open up your tooling to not just engineers, well, people can write Python in IPython notebooks like no other. Like it takes a day of learning, if you at most, to get it working. And this lack of startup cost is actually really important because traces are hard to work with. So the more barriers you remove, the better. So where does someone go from here after single trace analysis? Let's say they find that like these serial DB calls are they think that's what's slowing their new thing down. And how do you confirm that? Like you've only looked at a couple traces. Does that mean that you just got unlucky with the 5, 10 traces you opened and looked that up where it ran in your IPython notebook? That maybe those were the only ones with that problem? Well, the easiest way to do that is to provide engineers a tool to test that hypothesis. How long does DB calls take over 10 seconds? And what's really important is that snippet of code that formulates, that's the analysis that you got from the single trace analysis. It's important to be able to ship that off into somewhere to run over a large corpus of traces. That's important for 2 reasons. One, large corpus of traces gives you the signal that you need because you can actually say definitively, yes, this is my problem, and you can correlate DB over 10 seconds with overall latency or something, or error rate or something like that. But more importantly, this removes a source of friction that you don't really need to, like, let's say I'm a data analyst and I actually I don't know C++, I don't know Java, I just know Python. Well, this little snippet that I had that worked over there also works over here. And this is just a barrier removed from working with tracing. For this batch analysis, we have a way of, we basically have a kind of thing like AWS Lambda at Facebook that runs arbitrary Python. And we place very generous limits on what scope of jobs you can run. So you just submit it, and it runs with some priority sometime in the future, and you'll get an email back with the results. And this flow actually works pretty well and kind of like allows people to fire off a couple hypotheses, look at them later, see what's going on. The last piece of the puzzle is then stream analysis. Basically, once you have this analysis code, these little snippets that you find to be very high signal, maybe you want to run them continuously. Maybe you want to generate automatic reports to show how well has your team done in optimizing this over the course of a half. That's definitely one use case. Maybe you want to generate alerts based on this because you don't want this to show up again. You want to be informed if it shows up again. Like perhaps it's like an anti-pattern code that's really easy to make. Perhaps you just want to visualize it in the dashboard somewhere and you like, I don't know, like if the arrow's up and to the right, things are good. As soon as it crashes down, you need to like dive in deeper. Whatever happens to be, typically these use cases are the high signal use cases and therefore have the highest friction to write. And purposefully in these use cases, we actually try to lower the single trace and batch analysis. We lower the friction it takes to actually write analysis. And the reason for that is we don't want to drive people away before they get the signal that they need. We want to make it easy for them to get information out of their traces. But if you want to commit code and run this continuously without supervision or with a lower amount of supervision, you need to make sure that it is going to be useful. And so, but the neat part is still that no matter what, the same kernel of code, the same analysis works in all 3 cases. So then people can go back and say, oh, this stream analysis has some useful information. I want to build on top of this. Let's experiment. They go back to single trace analysis and they could be able to build on top of the stream's results in single notebooks. And so as a result, because everything shares the same code, this was actually the most important thing in this suite of tools, that you never get this isolation of like analysis that only belongs in one flow. Because what invariably people want to do is always jump between stream analysis and batch analysis and ad hoc analysis and tweak little things here and there. And they don't want to rebuild and reinvent the wheel every time. Furthermore, another side benefit of splitting these up into separate tools, and we learned this by experience because the first time we built this, it was one tool, is that these different tools have different goals. Single trace analysis and batch analysis, it needs to be usable. It needs to be really fast and really friendly for users. Stream analysis, less so. For stream analysis, you need to be able to have continuous alarming and insights on how well is my pipeline doing? Is it healthy? For a single trace analysis, there is no pipeline, so you don't really need that. There's other things that make sense for one versus the other, like memoization, for instance, or partial trace fetching makes a lot of sense when you know exactly what you're looking at. But if you're in explore mode, if you're in single trace analysis mode, that does not make sense at all. And by splitting into different tools, we actually were able to make these tools, optimize these tools specifically for the use case that they're designed for. And why is this important? Well, the first time we tried to tackle this, we built something called TraceQL, which is a trace processing and language system. This is an example syntax for it. It is built as a sequence of pipes. You can think of them as like Unix like commands, and you pipe them into each other, and except the things that flow through it aren't lines, it's trace objects, or trace points or blocks or whatever. We then realized somewhere down the line that we actually needed to build an interactive tool because people wanted to explore, and we just took the same thing and rewrapped it and said, here you go. We built a web-based UI around it. It was nifty. And then when we found that people wanted to rerun analysis over a large corpus of traces, we rewrapped it again and we said, here you go, just enjoy. And the result was an unusable, unmaintainable mess where this took like a week to learn. And so anytime someone wanted to make a modification to their team's analysis code, God help them. Like they pretty much have to consult with us to understand what it was doing before and how to add whatever they want to add and make it do the right thing. And furthermore, we were unable to effectively work with the stream processing code because every time we touched that, it had so many implications on all of these other tools that we weren't sure if we were breaking someone else's workflow just by making this optimization that was, a good optimization, optimization that we should have. So with this new system, by splitting into different tools, our hands are no longer tied. The shared code, the thing that's shared between all these different systems, is limited to the customer analysis code. So from their perspective, it's one code that they write that gets shipped everywhere and works everywhere. But from our side, we can do stuff like for our stream analysis, like we can add how caches for traces. We can like dynamically size the executors that run their stuff. We can like prioritize pause low priority executors when things are under heavy load. We can do all sorts of cool things that we just could not before because we repackaged the same thing. So lessons we learned that people definitely want to build tools on top of tracing. Like people have really, really interesting ideas, really dynamic, cool tools specific to some use cases, general and others, that are really cool, and tracing is the thing that they want to store the data with. But at the same time, traces, because of the almost homogeneity but still heterogeneity of systems at Facebook, it's hard to understand and work with. And therefore, to a person relearning tracing or being introduced to the first time, it could be intimidating. And so as a result, your tooling needs to help them along the way as best as possible. And if you build a do-it-all tool, it's going to take a power user to make good use of it. And finally, infra teams aren't great at building user-friendly tools. So get feedback, get help often. make sure the customer is involved in building the tool.